Thanks HexAuFoil for inviting me to join Peter Harrison and Félix Weis to hold this webinar. My name is Julio Ortiz. I am Senior Software Product Marketing Manager at ThermoFisher, and I'm happy to have this opportunity to talk about our software for automated data collection in CryoEM, EPU, in the context of the new HexAuFoil grids. We welcome this new QuantiFoil product, as in ThermoFisher Scientific, we are committed to facilitate the data acquisition process using different sample carriers and EPU to improve data quality. I will cover some basics while I let my colleagues go into details. Thermo Scientific EPU software is designed to be user-friendly. The software user interface presents the main step for an acquisition run in a logical organized sequence, which simplifies the setup process. The home page is primarily used to quickly load predetermined settings. The preparation tab is where the optics, camera settings, and related calibrations are specified. In the Atlas tab, you can create an overview or map of a specimen by stitching images of low magnification. The auto functions provide various automated tasks being used during the setting and execution of the workflow. And finally, for setting up and running acquisition sessions, you have the EPU acquisition tab. It is easy to be trained in EPU, and the setup of that acquisition session for one grid is possible in less than 30 minutes. We provide quarterly releases to keep the software updated, incorporating each time new functionalities. Just to mention an example, relevant for today's topic, in the newest EPU version, we introduce a data acquisition mode using plasma peak imaging for those systems equipped with our Selectris or Selectix energy filters. The conventional zero loss imaging applied to wall grids presents a challenge for the microscopist. It's not so easy to discriminate foil holes based on their ice thickness, something that is straightforward for carbon foil supports. Fortunately, Wim Hagen, being at the EMB at Heidelberg and before joining our company, proposed a method to make a better usage of the dynamic range of the low magnification images, the plasma peak imaging. Basically, a change in the high tension offset of the filter prisma causes that inelastically scattered electrons form an image that is very suitable to distinguish differences on eye thickness, with the understanding that the contrast is inverted. You may want to select dark gray holes. Well, we have implemented a plasma peak imaging mode in EPU 3.8, the version that we are currently promoting in these days. In the preparation tab, you adjust preset for Atlas using counting mode. Then you enable the plasma imaging and acquire a preview. You will see an example of a plasma image with the empty foil holes in black. Then you can adjust the preset also for grid square using counting mode. First, you will see here the zero loss image, and if you enable the plasma imaging and acquire a preview, you get the inverted contrast in the plasma peak imaging. This is an example of an atlas taken with plasma image mode, and then you can proceed with the setup of an automated session. These presets are going to be used in the different tasks that you need to follow. For example, in the whole selection, whenever you acquire an image in plasma peak mode, then you have both images, and you can visualize both images by sliding a tool to visualize the two different images, zero loss and plasma image. Then you can measure the foil hole size and find the holes. The algorithm will be used the zero loss image. But then when you want to classify and select the foil holes using the filter as quality, the algorithm will use the plasma peak image. That is the sense of the whole method. As you see, this movie was done using a square gold grid, but the plasmon imaging can be applied to other geometries. Thanks to an early collaboration with Quantifoil, we offer support for HexAuFoil grids since EPU 3.1. All functionalities that I presented you before for square gold grids are also available for hexagonal gold grids. This is an atlas tile in plasmon imaging. Then you can apply these presets to generate the atlas, and the classification of grid hexagons works. Then in a session you need to select the grid type holy gold and the geometry type hexagonal. Then you can measure the hole size as usual, define holes, remove holes close to the grid bar, and filter ice quality. Everything is working to select the holes. In fast screening you can select representative holes also. And depending on systems, you might need to skip holes in hole selection, because for example in the glaciers or in the tundra, the beam size diameter will be so large that you might irradiate neighbor holes, so then you need to skip some holes. And finally, this is a demo of the EPU run, in which you see that the program is acquiring high resolution images as you are used to for other grid types. In our portfolio, we offer also EPU Multigrid, a program for queuing EPU sessions. After you have set up a session for one grid, for example using the fast screening function, you can apply very easily the same settings to those grids in the autoloader with same geometry. And you can combine screening and data acquisition session, changing parameters. Overall, this helps you to increase efficiency, to save time in the setup, but also by allowing many short runs overnight or long runs during the weekend. Aiming to increase further efficiency in CryoEM, we introduced Smart EPU a couple of years ago. It adds image evaluation capabilities to EPU with two alternative programs, Quality Monitor or Embedded CryoSpar Live. And important for our discussion, the software make use of deep learning algorithms to automatize the setup and monitoring of EPU runs. Our first smart plugin was the Smart Filter to discriminate highly contaminated or broken foil holes from those adequate for image collection. This year we released two other plugins that use trained neural networks, a smart selection of grid squares to automatically classify grid squares, and a smart eye thickness prediction to group detected foil holes by absolute eye thickness. We are currently developing a smart hole finder, which will automatize the task of finding holes. Currently, these plugins are working on carbon grids, but of course we will extend their applicability to gold grids. We are already started the training with HexAuFoil grids. With all these smart plugins in place, we are confident that by the end of 2024, we will support autonomous screening of a whole grid cassette with only a few clicks. This will allow you to take full advantage of the high throughput of your cryo-temps. Coming to an end, I would like to highlight this article from Basil Kreber's lab at the Institute of Cancer Research in London with the participation of some colleagues at ThermoFisher. Using our tools, they presented a protocol to efficient screening of samples, complexes between the CDK activating kinase and several small inhibitors. With only one 1-hour data set, they can achieve a structure with sufficient resolution to identify the bone inhibitor, and they produce 24 of these structures in 24 hours. With more time, you can reach 2.9 angstrom in a glacius, and for very high resolution, they collect 10 hours data sets in a cryos. The CryoEM specimens were prepared on HexAuFoil grids, QuantiFoil also. I can wait to see further improvement in this type of experiments with the HexAuFoil grids achieving higher resolution or reducing the number of images required. I would like to take the opportunity to promote another webinar in which we will be talking about our rebranding solution for data integration in CryoEM called CryoFlow. It is the successor of Athena. The webinar is on June 11th, so you still have the chance to register. We are presenting technical details and more information about the application supported by this platform. Please don't miss it. To finish, I would like to thank my colleagues at QuantiFoil and ThermoFisher involved in these developments and you for your attention. Thank you.
For that lovely introduction to the upcoming improvements to EPU that will help with getting the best out of Hexafoil grids and enable your data collection to be really fast and efficient. It was a fascinating insight, and I'm sure plenty of our listeners will want to come to your webinar next week as well. We're now going to move on to Peter Harrison from eBIC at the High-Wyl Research Campus, and he's going to tell us about what they've been doing to explore the optimum settings for data collection for using Hexafoil grids with EPU as it stands at the moment, both on Krios and Tundra instruments. Peter, off you go.
Hello everyone, and thank you Claire for the invite to give this short talk. So I want to quickly talk to you about the microscope setup we use for Hexafoil grids here at eBIC. So my name is Peter Harrison, and I'm an electron microscopy scientist here at Diamond Light Source, which, for those of you who don't know, we're the UK's National Synchrotron Facility, located just outside of Harwell. And we're also home to the National Biological Cryoimaging Facility at eBIC. So I've sort of got two halves to this talk. Part one, I'm just going to go through the basic settings which we employ in the image presets. And then in the second half, I'm going to talk about some additional settings which we try and take into account when we work with hexafoils, both on the Krios microscope, but also on our 200 kV Glacius microscopes. And this is some work that's been done by our industry team, in particular Hazel. So, part one. I'll just give you a brief introduction as what instruments we've done this work on. We're really lucky here to have a wide variety of different microscopes, and we support all types of EM from SPA to tomography to ED. We have 5 Krioses equipped with a mix of K3 bioquantums and Falcon 4 Isolectris X. And the work that I'm going to show you today has been done primarily on Krios 4, which has a K3 bioquantum, and Glacius 1 from the industry group, which has a Falcon 4i detector. And for anyone that's interested on Krios 4, this was all done in EPU version 3.7. So the first thing I really want to make a point about is the plunge freezing. We've not done a lot of extensive optimization around this, but we have found when we have made Hexafoil grids that the recommended settings provided by QuantiFoil work quite well. Important thing to note though is flatness of the grids we find is important. So it's worth keeping an eye out for that, although we also find that they're pretty robust in comparison to other grids, so that's quite nice. So I'll start off with the Atlas and grid square, or grid hexagon, if you will, settings. So first off, we don't change anything for the Atlas mag, that stays the same, and it works totally fine. We do, however, make a slight change at the grid square mag settings, and this is mainly around the amount of defocus we apply. So at grid square mag, we're applying only 10 microns of defocus, and you can see it doesn't make a huge difference. This image down the bottom is taken with our Hexafoil settings applied. This one at the top is taken with our quote-unquote normal settings, which we use for more regular QuantiFoil grids. And you can see there's not a big difference, and there's enough contrast in there for us to be able to work quite well. So I've shown here the settings that we've used. Obviously this is dependent on your things like your gun strength, and although that should be reasonably consistent between microscopes, these values really are only for reference. So your setup may be slightly different. The whole eccentric mag is where things start to get a little bit more involved and important. So this image here on the left is an image taken at what we use for our normal settings. So this is about 13,500 X mag. And you can see we're imaging quite a large area. I was always taught you want, at this mag, you want one hole and then bits of surrounding holes. So we're quite far out. And obviously the intuitive thing to do is to increase the mag to get that single hole in the image. And that's what we see here in the second image. This looks quite nice, and 42,000 is actually the mag we use for this. It's important here to make a few adjustments to the size of the beam and the dose. So this is the illuminated area at 42,000 without any beam size adjustment. So you can see we're pre-exposing quite a wide area of the grid square, which we don't want to do. So we suggest making the beam smaller, so you're only imaging the area that you need. But it's important at this point to really take into account the dose and measure the dose. So we would suggest that you make sure your dose on the whole eccentric setting is below 10 electrons per nanometer square to avoid overexposing your sample too much. Now, it's important to note here that when you start the collection, the microscope is going to take several images at this magnification to do things like the APHIS calibration and do the autofocus. So your start-off area will get a bit more exposed, and you really want to make sure your beam is not too big at this stage to make sure that you're really not overexposing your grid too much. So this is just a summary of basically what I think I've just said. Make sure you adjust the beam size, the beam settings rather, to account for the smaller illumination area. The other thing we've done here, similar to the grid square setting, is we've lowered the defocus, and this is more important later on when the collection is actually happening. This is because when you apply a defocus, you actually get a slight rotation of the image. And at the center where you do the autofocusing, this is not so much of an issue, but as the imaging moves further away from that autofocusing position, this rotation will become more pronounced, and what will happen is you will end up missing the holes that you're trying to image. So we try and lower the defocus to make that rotation as small as possible. You may have to offset this with a little bit more dose to provide you with the contrast that you need to find the holes, but without providing too much dose to overexpose your sample. So data acquisition and autofocus settings, these are the last two imaging settings that you really need to consider. On our CRAS with K3 Bioquantum, we recommend imaging at 165 mag, so that's about 0.497 angstroms per pixel. So there are some things to consider here. At this mag you will hit a bit more of the support, but because the beam is slightly larger, you're more likely to hit the target. On the flip side, you can go to a higher mag, such as 215, which will get you more of the hole, but on the flip side, if things are not quite aligned properly, you may end up missing the hole, and so end up imaging less. And this is why calibrations are really important, which I'll come on to shortly. It really is a case of what works for you, and it may depend on how much gold and support you want within the image. The main thing is to make sure that your beam is bigger than the hole, and then you're getting the equal illumination across the entire hole, which is one of the benefits we have with these small hole sizes. The only other thing I want to draw your attention to here is the autofocus area. So we use a different mag size for autofocus and for the data acquisition image, and this is just so that we can make the beam size a little bit smaller, and that we're not exposing adjacent holes when we're running the autofocus. The autofocus routine will only run a dozen or so times at most per grid square, so it's not the end of the world if you accidentally image an adjacent hole, but we try and minimize that by going for the smaller beam size. So part two. So the first thing I want to talk about is the eccentric height routine, and we find that this works really well if the grid Z height is already not too far, so not a million miles away from the eccentric height. So we find if it is far off, the auto routine will fail, and we generally do auto eccentric by beam tilt. We find that generally works quite well. And so for this reason, we suggest as you're running the auto-eccentric routine to just keep an eye on it as it's happening. I'll be the first to admit that I tend to go and make a cup of coffee while this is running and then come back and assume as long as it's worked, it's fine. But really with Hexafoils, we suggest just keep an eye on it. And then as it's happening, you can make an assessment of whether it's working as it should be. And it's for this reason that when you're doing the prepare all squares setting in routine in EPU, because it doesn't show you the autofocus routine as it's happening, it's worth going back once that's finished and just checking the eccentric height of a few squares manually to check that they are as they should be. And so I mentioned it earlier, but the flatness of the grid is also important here. So these two images that you can see flipping at the bottom, what I did here was I went to the center of this grid square and I ran the auto-eccentric height routine, and it was fine. And then I moved to the extremes of the square at the top and the bottom just to assess how far out of eccentric it was in those positions. And you can see at the bottom we're pretty good. At the top we're a little bit further out. In reality, this here on the right hand side is not going to be so far out that it will massively affect the collection. But you can see that it's not always perfect at the extremes of your square. And so if your grid wasn't quite so flat, this would be more pronounced and it would have more of an effect on your data collection. So it's worth keeping an eye on this. Image shift calibrations, these are really important, and we have found that they need to be absolutely spot on. One thing to note is because we tend to work with a little less defocus, the result of that is that we have less contrast in our images. And so it can be slightly harder to find features on the grid. And so because of this, what I tend to do is I tend to find more isolated bits of dirt on the grid, and I find it's easier to find these. So you can see here in the top right image, rather than go for this bit down here on the right hand side, which is intuitively what I would normally go for, I've gone for this more isolated bit of dirt because I can isolate it to that single hole, and that makes doing the image shift calibration routine a lot easier. So carrying on with the image shift calibrations, we would suggest that it's really important when you're starting a new session to redo the image shift calibrations. And this is because small deviations can have a big effect. On this left-hand image, I put a Hexafoil grid in after someone had finished their session and tried to target the center of a hole. And as you can see, I ended up about 145 nanometers off, which meant that I missed about, over half of the hole. So this really isn't ideal. And then on the right-hand side, I redid the image shift calibrations, again, targeting the center of the hole. And you can see I'm still 26 nanometers out, but I've got much better coverage of the hole. And so you can see this is why it's really important to be accurate. If I was just 50 nanometers out, that doesn't seem like a lot, and it really is not a lot. But it's about 1/6 of the hole. So you really need to be accurate with your image shift calibrations. And so it's really important. You may want to repeat them several times to make sure that they're as accurate as you can get them. So next we come on to the session setup, and I'm not going to go into a huge amount of detail, as for the most part this is all the same as you would do normally. But again, you need to be aware of the flatness of the grid. And so for this, what we tend to do is we tend to pick squares within the middle of the grid and squares which are close together, so we don't go to the extremes of the grid if we can avoid it. And we find that this works really well for us. I mentioned it before, but once you've done the session setup, manually check the eccentric height on a few grid squares to check that everything's as it should be. When you do the hole size calibration, when you're doing the hole selection, just make sure that that circle is as accurate as it can be, and then you shouldn't have any troubles with the software finding the holes. Again, we find that that usually works pretty well in EPU. This image here on the right hand side these are the APHIS collection groups that the microscope set up for this hexagon. And you can see for the APHIS collection, it split the square up into about 9 regions. So what happens here, for those that don't know, is that the microscope moves to the middle of this region, it runs the autofocus routine, and then it uses APHIS to image all of the other holes around. What the microscope's trying to do here is it's trying to minimize the amount of stage movement that it has to do to image each hexagon. So for this, what I did was I had the APHIS collection range set to 12 microns. That doesn't mean the biggest amount of beam shift will be 12 microns, but that's the most it will do. But the point I'm trying to make here is that this is why you need your setup to be as good as you can be, because if it's not, these holes that you image at the extremes, you'll be missing the hole and it won't be as good. The other thing to note here is that the calibration for this is done on a per square basis. So if your grid is bad, all of the holes will be bad. So I know I've said it many times, but you need to make sure your image shift calibrations and all your other setup is done properly to get the best data that you can. So just to show you how this actually looks when we go through and do it, this is a test collection that I did, and using our setup with the K3, the theoretical maximum imageable area for each hole is about 86%. You can see this hole here right in the middle of the collection range is pretty good. We're imaging most of the hole, which is that we want. And then this hole down here, this is about 10 microns away from the autofocus area. You can see we're still imaging most of the hole. And actually on this collection, what we did was we went back our data analysis team, led by Dan Hatton, actually did quite a nice job of running some maths for us and checking to see what percentage of the whole was imaged in each movie. And you can see we're getting most of our images in the area that we would want. So that's really nice. Our collection rate also pretty good, 720 movies an hour in CDS mode. So we're pretty happy with that. So the last thing that I want to talk about is using Hexafoils on a glacious microscope. And this is work that's been done by Hazel Atkinhead in our eBIC for Industry team. So again, she's been through and found all the nice settings, like I've done on the glaciers. Again, no, not huge defocus values, and also the amount of dose. So the whole eccentric down to 5 electrons per nanometer square. And you can see how this looks quite nice. We still got enough contrast to find the holes. The other nice thing is with the 4-eye camera, because it's square, you tend to be able to get more of the hole in the field of view, which is quite nice. So the other important thing to consider when using the glaciers is the hole selection. So we found that it's best to image every third hole. You can image every second hole, but you can see here with the size of the beam, you do risk pre-exposure. So that's an entirely personal decision. Make sure the autofocus area is not over the area you wish to image. This is less of an issue now with the latest updates on EPU. And the other thing that Hazel's looked at is the APHIS range versus collection rate versus accuracy. And she's found that 6 microns APHIS range gives pretty good accuracy, and it's the best trade-off between accuracy and collection rate. But again, this is something you may need to play around with your microscope. I'd just like to finish by thanking everyone who's helped with this. So David Owen, Dan Hatton, Stephen, Dan Clare, and the rest of the eBIC team. And Hazel and Jason in eBIC 4i, and Miriam at SPT LabTech. And thank you for listening.
Thank you, Peter. That's really useful information, and I'm sure a lot of our viewers today will get a lot of help from that with their own data collections. Our now final speaker for this afternoon is Félix Weis of the IBS in Grenoble, and he's going to talk about using Hexafoil with some interesting real-life examples, so not apoferritin but some other proteins, and how they've benefited him in his research. Thank you, Félix.
Hi everyone, it's my great pleasure to be here today. I first would like to thank Claire for inviting me for this webinar. And today I will talk about my first hands-on experience with Hexafoil grids. And I would like also to apologize for any redundancies with the other talks. So I'm a CryoEM scientist at IBS in Grenoble, which is an institute dedicated to structural biology. And we are very lucky to be on site with all the instruments for structural biology, including a neutron source and, of course, a synchrotron. And CryoEM-wise, on the site, we have a glacios at IBS. There is a second glacios at the Humble outstation in Grenoble. And within ESRF, there is 2 Titan cryos, including G4 with Coldfake, Selectris X energy filter, and Falcon 4i. The first sample I would like to talk about today was a kind gift from Anna, which is with a PhD student in Bruno Franzetti group. It was actually a leftover of a purification she was not happy about, and I'm quite lucky because it did happen to be a very nice sample. So I won't talk too much about the sample because most of them are not published. So basically it's a half megadalton complex, quite high symmetry, tetrahedral, T symmetry, then concentration and buffer-wise, all fine. Regarding freezing, I just use a Vitrobot with classical freezing settings, except that I just followed the recommendation from Quantifoil. So basically, I did glow discharge in a glow cube twice longer, 80 seconds in this case, compared to ultrafoil grids, and also use the blood time slightly longer of 5 seconds instead of 3 seconds normally. I then loaded the grid on our glaciers equipped with a K2 camera. And you can see on the left here the atlas, the grid map looks quite nice with many squares. And if we look at one square in particular, many holes, and they happen to be all icy. You have ice everywhere, and actually most of the squares, if not all the squares that were actually looking good on the grid map on the atlas were actually containing very good ice. In terms of acquisition settings, so the particularity of our glaciers is that it has a K2, no energy filter, so we can't use EPU, so we are using actually CryoEM. And also there is no fringe-free imaging, so we have actually fringes, so we are in this situation. So of course we have to use quite a large beam to avoid seeing fringes. Otherwise, it's basically very classical imaging settings. K2, so it's K2 camera. We use rather long exposure time because the dose rate has to be quite low. We're here at 3 electrons per pixel per second. Since the holes are quite small, and so that's a Hexafoil grid. So basically the diameter of the hole is around 300 nanometer. We use quite a small pixel size, high magnification. So we were at 0.9 angstrom per pixel here. And you already see the particles here. So what also interesting in our configuration is a acquisition pattern. So since we had quite a very large beam size, so in here for this session, it was more than 2 microns. So here the pink square corresponds to the camera chip, to the actual image. And the green circle is a beam. Okay, so it's a burned area for each shot. And of course, we would like to avoid that an imaged hole is exposed twice. So here, basically, to also increase the throughput, we use a 3x3 pattern. So basically, it's 9 shots per stage movement, per stage position. And in that case, we had to space quite a lot the shots to avoid burning images twice. So it means basically for 9 holes acquired, we're burning 121 holes. Still, despite wasting so many good ice, we were able to record between 250 and 300 images per square, which is quite reasonable, I think. And with just a quick and dirty overnight data acquisition, the dataset, this initial dataset was over 3,600 images. Processing, I won't spend too much time on it. Very classical, so good. All pre-processing, picking, classification, and initial 3D refinement were done with Relion. Maybe one thing, it's about the picking. Despite we are still seeing gold on the images, we're still seeing the foil. It's quite easy to, by playing with the parameters, to avoid picking on the gold and only pick particles in the ice. So that was quite straightforward. You can see reasonable 2D classes with high resolution features visible. And then the polished particle in Relion were imported in CryoSpark for a final run of homogeneous refinement. And the final map was sub 3 angstrom, actually 2.6 angstrom resolution, and a quick de novo model building with Model Angelo worked very, very well, even without sequence provided. And you can see a very nice resolution. You can clearly see the beta strands nicely separated in that case. Then next step was to look at this grid on the Titan Cryos, so on our newly installed Cryos G4. So since we have an imaging filter, we could use plasmon imaging for the square maps. So I won't spend too much time explaining on it, but basically we are doing plasmon imaging instead of zero loss imaging at the square level. And it allows us to look at the eye thickness very carefully. Basically, the empty holes, no eyes will be black, and then the whiter it gets, the thicker it is. And here you can see on this typical square on the very same grid we use on the glacier session, all the holes had ice with a very rather thin ice and very uniformly thin ice everywhere. Then on the CryoSG4, we're using EPU for acquisition. So since we have a fringe-free imaging option, we were able to use a very small beam, basically the size of the hole. So we could reduce the increase magnification and reduce pixel size. So typically we use a 0.5 angstrom pixel size. And so this was a very quick and dirty setup. It was actually the very first sample we imaged on the microscope. And so basically I just use a 1 second exposure. So the total dose was quite low, around 20 angstrom per 20 electron per square angstrom, a typical image. So you can still, at low defocus, particles are still visible. And just over a coffee time, 10-15 minutes, we were already able to acquire 200 images. A quick processing of these images led to a spectacular resolution, so 1.9 angstrom resolution. And you can see very nice features of the side chains here. And it's quite nice because there are not so many non-apophylated sample below 2 angstrom on the EMDB. So it was a very good surprise. The next thing I tried, or we tried, and because we are getting more and more requests, is to try tilting the Hexafoil. Since they are supposed to be very stable, we are still on the very same grid with this half megadalton protease. I tried tilting. So why do we tilt is, of course, to get missing information of the missing views in case of preferential orientations. The problem is you increase movement because in theory, upon electron exposure, the ice is buckling. And when you tilt, this movement is translated in X and Y movement. So you have more particles movement upon exposure. Nevertheless, we did data acquisition. So that's again a plasmon imaging square. Again, you can see very thin ice everywhere. You see it slightly thicker on the edge, it's slightly whiter as expected. So we, of course, only acquired the central part of the square, or the hexagon in this case, of course. When you tilt, you can't really use a very high image shift, beam shift movement in order to increase your quality of the images. So basically, I just use this setting. So basically 7 acquisition per stage movement. So it was a bit slower. Still, we managed to get 250 images per hour. So, and after just overnight data collection, so a few thousand images, I could obtain, following the same processing protocol, a reasonable 2.1 angstrom resolution. I didn't push it. I guess I could most likely go below 2 angstrom with more classification and tricks here and there. What about movement? So you can see on the left, indeed, with no tilt, there is hardly any movement upon exposure of the particles when you do motion correction of frame alignment. Still, when you tilt, you see you have movement. So basically 10 times more movement upon frame. So despite having a nice Hexafoil, nice geometry of the grid, you still see movement, but you can still process everything and of course correct for it. So that was one sample. We are also spreading this grid. So now this, I would say, the Hexafoil are more and more used within the institute. So I will just give a couple of examples. So that's a nice sample. It's a yeast pathogen protein around 200 kilodalton. So that's a work done by my colleague Lefteris from the EM platform in collaboration with Vincent Chaptal and Lionel Balu in Lyon. And again, you obtain very nice grids, very thin ice, very uniform, very homogeneous. That's a typical image. You can nicely see the particles, and a quick and dirty, not dirty, but let's say a quick processing of only a small part of the images already led to a 3-angstrom resolution map. So we are quite confident it will go quite far in terms of resolution. Another one, interesting one, it's an extremely small protein. So it's a protein, no membrane, no micelle, no nanodisk, no DNA, no RNA. It's a 6-ish kilodalton protein. You hardly see them in the eyes. It was a quite low defocus image. So that's a sample from Rebecca Wild and her student Rebecca Jo Bustani, and still ongoing processing, but you already see that the 2D classes are extremely promising, and you can already see quite convincing secondary features, alpha helices and beta strands on the 2D classes, and we have good hope that it should lead to a sub-3 angstrom, 2 angstrom map for this extremely small sample. So just to conclude and maybe to summarize, so far we are quite happy with the Hexafoil grid. They tend to give extremely thin ice and very uniform among the grid. We hardly see any empty holes. Reproducibility is very high in terms of blotting and freezing parameter with the same sample. So it means that we hardly optimize freezing condition and also screening and acquisition when you set up data collection makes things faster and very easy, especially with automated hole selection in EPU, for instance. We could, even with without the fringe-free imaging option, like on our glaciers, data acquisition was still possible and quite efficient with still 200, 300 images per square. Tilted acquisition was possible, so I tested 30 degrees. I presented 30 degrees here, also did some preliminary tests at 40 degrees, and also did run like a charm. The only thing is, since we have very small holes, we are 290 nanometer according to the catalog, your beam shift image shift calibration has to be quite accurate, especially when you are using the faster option in EPU, when you move up to 10, 15, 20 micron beam shift image shift. So could be interesting in EPU to have an option to reduce this shift in order to be more accurate, because maybe even a 15 nanometer offset in hole centering, then it's already, you start to see a lot of ice and you lose a lot of particles. So I would like quickly to thank all the people involved in the slide I presented you for. So first of all, of course, my Guy Schoen, the head of the group, of the EM group in Grenoble, who really spent the last decades to set up an extremely nice CryoEM environment in the institute and also in Grenoble. All the people of IBS EM platform, the CM02 team, which is a new cryos at ESRF, and also the people, the collaborators who kindly provided the samples or their results with the Hexafoil grids. And that also just a quick look of some images done on a viral polymerase within the lab with Hélène Mallet and her student Quentin Paco. And with that, I thank you for your attention. I'm happy to take questions.